Hello, everyone. Welcome. We'll get started in a few minutes here. Welcome to those of you who are just joining us. We're going to get started in a moment. All right. Hello. My name is Elizabeth Angel. I'm EERI's Communications and Program Manager. Welcome to today's second Quake briefing in our series on the Japan earthquake that struck on New Year's Day this year. This session will focus on buildings and lifelines damage. And this series, as always, is hosted by the Northern California Regional Chapter. Before we get going, I want to take a moment, just for those of you who may not be familiar with the EERI, to introduce us. The Earthquake Engineering Research Institute is the leading nonprofit organization working together to bring together people from a wide range of disciplines and regions who are joined by the mission of better understanding earthquake risk and increasing resilience to earthquake hazards, both in the US and around the world. So if you'd like to find out more about us, I'll share a link in the chat. We're always welcoming new members and would love to have folks get involved with our work. This webinar series is hosted by our Northern California chapter, and I'm going to turn it over to Richard McCarthy, president of the chapter.
Thank you, everyone. And on behalf of our chapter, welcome to our speakers. Our chapter has many dedicated specialists that have devoted basically their lives to reducing losses from earthquakes and speeding economic recovery. And because of our proximity or closeness to the state capital, it provides our chapter the unique opportunity to reach out to some of our state decision makers. So I'm going to turn this over now. Thank you again to Bruce Mason, who's headed up this seminar or this webinar. Personally, thank you, Bruce, for taking care of this, making sure this is going to be successful. And I know it will. Thank you.
Thank you. I want to welcome everyone to our briefing on the magnitude 7.5 Noto earthquake that struck Japan earlier this year. This is the part 2 briefing, and it'll be dealing with building and infrastructure lifeline systems. My name is Bruce Mason. I am one of the executive board members of the Northern California chapter, and I'll be serving as your moderator today. Now, our briefing program is a free public service. It's available to anyone that wants to view. Our goal is to share key information about earthquakes worldwide, as well as to develop a mechanism by which the earthquake community can develop contacts with researchers and engineers in other countries. So if you're a member of EERI, you will receive notifications of future briefings. But if you're not, you can still get on our mailing list. And how you do that is to send me your email address as shown on this slide. Now, all of our previous briefings are available on the YouTube channel, and you can go there, and if you type in Quake briefing, a listing of them will appear. Now, on to the earthquake. The earthquake struck in the afternoon on January 1st on the west coast of Japan. It caused extensive damage, with direct damage costs estimated as high as 18 billion US dollars. That's billion US dollars. There was extensive damage to buildings, homes, ports, you name it. All kinds of infrastructure was damaged. Our part 1 briefing that occurred in February dealt with the strong motions recorded during this earthquake, as well as the spectacular geotechnical ground failure aspects. We are excited in our second briefing today to have 2 speakers joining us from Japan who has done extensive field investigations after this earthquake. The first speaker will be talking about the causes of damage to buildings, and our second speaker will be talking about damage to lifeline systems. Our program today is 60 minutes. Each of our speakers will talk for about 20 minutes each, and the remainder time will be devoted to question and answers. You, the audience, are encouraged to send questions to the speakers. And how you do that is you will press the Q&A button you see at the bottom of your screen, type in your question, and then behind the scenes, another one of our executive board members, Tali Feinstein, will compile these questions, and then she will appear in our program later and will pose the questions to our speakers. Now, we recognize we might have more questions than time allows, so each of our speakers today has kindly provided their email address, and you'll see it in their presentation, so you can send them questions directly. And in the coming days, they will try to answer your questions. Now, I would like to introduce our first speaker, Dr. Masahiro Kurata of Kyoto University. Dr. Kurata, please proceed.
Thank you, Bruce. Do you see my screen?
We do, but you're not in slideshow mode yet.
Okay,
There we go. Great.
ready? Okay. Thank you for the introductions. First of all, my sympathies go to the victims and those affected by this great disaster. And it is a great honor for me to give a briefing at your California chapter of EERI. I actually served for EERI. This is my experience with EERI. I went to Georgia Tech for my PhD and had a good opportunity to be involved in the chapter activities, and it's established my career now. So I really want to use this opportunity to thank EERI. Now let's move into this earthquake. The earthquake affected the very large area of the Noto Peninsula, which is the west coast of Japan. The Noto Peninsula is about like 75 kilometers in length, and the severely affected area was this Noto Peninsula in Ishikawa Prefecture. However, about 300 kilometers in width area was damaged with the 5 or 5+ intensity in Japanese meteorological agency scale. This caused some liquefaction in these entire areas, and that's also increased the damage caused by the earthquake. And compared to the most recent earthquake in Japan, 2018 Osaka Hokuba earthquake, the scale is much larger. The Osaka Hokubu earthquake actually was only MJ6.1, but paralyzed the Osaka city area. The economic loss was in Osaka area was actually higher than 2016 Kumamoto earthquake, but this time the economic loss may be even higher. So this is the characteristics of the event. As of April 23rd, casualty was 145, housing damage of 78,000. Non-residential, the building damage is 23,000. And strong shaking with JMA intensity of 7 was recorded in Wajima, which is the left top side of the Noto Peninsula, and then Shika town. And the crustal deformation was very significant. Actually, in Wajima area, the port facility was up by 4 meters. So now there's no water in port. This region was known as earthquake swarm. In the most recent, the notable one was in 2007 with magnitude 6.9. And also the last year in May, they had a magnitude 6.5 earthquake. And this time earthquake warning system worked correctly. As in some region, it didn't reach on time, but after like 10 to 20 seconds, earthquake warning was triggered. That helped people to prepare for the strong shaking. A little bit about the seismic damage in seismic design in Japan. New building law was enforced in 1981. From that time, the building is designed for two levels. Level 1 is for serviceability for about the return period of approximately 50 years earthquake. Level 2 is the safety limit for the very rare earthquake with the return period of approximately 500 years. After Kobe earthquake, the government and also researchers noticed that the building built after 1981 had the lower collapse ratio and damage ratio, so that they made their acts for the promotion of seismic retrofit. Now the hospitals, shops, and hotels or schools, elderly care homes, many of them are seismically upgraded. And also for those buildings, even the private one, if the building built along the regional disaster response basis or evacuation route, they need to be diagnosed and then recommended to seismic retrofit. More recently, in 2018, after the Kumamoto earthquake in 2016, one new guideline of functionally continuity for disaster response space was issued. Now the government office, hospital, shelter, schools need to consider the functional continuity. This is the recorded ground motion. I believe the Professor Goto explained last time in the briefing about the ground motions. But in this the acceleration spectrum, I compare the recorded motion with the level 2 design strengths for building. It's about like 1G. So in the north side or northwest side of the Noto Peninsula, at most places the ground motion exceeded the design. And even in the lower part of the peninsula, the ground motion exceeded the level 1 design. So severe building damage was expected. A little bit more analysis on the ground motions. This is the figures for the suit accelerations and then spectral displacement relationship. If for the stiff building with the natural period of 0.2, 0.3, actually maybe the deformation was not so large. While we have a pulse type, the power in the period of 1 to 2 second range in this the spectrum. So if we consider the building with a little bit longer natural period, let's say 0.7 seconds, and in Japan, the steel buildings has 0.3 to 0.45 the base shear coefficient. So if we set the base shear coefficient for 0.45, the capacity spectra method provide us the large deformations expected to the steel buildings or timber building with a relatively longer period at some locations. We have conducted the reconnaissance survey at the area around the ground motion stations. And I will focus on the non-residential or non-wood structures or ground deformation around the structures. and the functionality of the disaster response bases or other large buildings. The survey team was the trip was departure was in approximately 2 weeks after the earthquake with DPRI colleagues, and later with the colleagues in Nagoya or Tokyo University, we conducted more detailed survey in the buildings. At the same time, we hosted Professor Khalid Mosalam of UC Berkeley from November to January. So we had opportunity to talk about this STEERI program for virtual reconnaissance report. And now we collaborate for their report. Survey was powered by this Fulcrum STEER applications provided by Professor Bosalam's team. So I recorded the photos and then the damage rate using their applications. For example, this is the Wajima City records. WJ01 in the very right, the green one is the strong ground motion stations. And then from there, I walked a little bit for like 2 hours and then recorded the damage of the buildings. The red is destructions, mostly the residential. And there are a few non-residential buildings because this is a kind of suburb in Japan. And I'm originally from the expertise in the steel structure. However, I only found like 3 steel buildings damaged at this site. This is the scenery of the town, drastically changed by earthquake. You see due to the liquefactions of the reclaimed soils, the lifeline systems uplifted. And then we see a lot of the complete collapse of the traditional the housing at these regions. And that time the temperature was very low, around like 1 to 2, and we had a snow warning. Also, a lot of the historical structures, including temples and shrine, was severely damaged. This is a photo of the typical traditional timber house in Japan. It's the moment resisting frame with walls as the shear resistant element. And normally the strength is calculated by the area of the wall. And on top of the roof, we have a so-called kawara. This is tile. And with strong accelerations, they displaced or the slip off. And those timber houses typically has a semi-rigid joint at the connections. More recent one has like the steel, the anchor, and then steel holder anchors, and then connections elements. But the traditional one, it typically has very low stiffness after some deformations. Some damage to the reinforced concrete buildings. On the left side, the 3-story or 4-story building looks okay from outside, but if we go close, they have like 20 centimeter the settlement, or sometimes uneven settlement, and those is the really big problem now, because the city is in Noto Peninsula, located at the coastline, and they have typically the very soft soil, the grounds. The right photo is the most kind of famous one from the media. One 7-story building collapsed completely. However, there is not many collapse of the non-residential buildings, and then this is the kind of exceptions. But now the investigation is going on, like why these piles are pulled off. Before the 2000 year of 2000, the design for the pile was not seismic, and then after 2000, seismic design is enforced. So there are some technical the problem for the old buildings in Japan, and that's it's difficult to retrofit. For the steel buildings, they are only mostly the low rises. They are subject to the severe ground shaking, and there may be the amplification due to the relatively softer, relatively longer the period of the structure. And they suffered from this cladding damage, very severe. And some they are the collapse, but they are aged and then with some very small sections of the column, so they are seismically deficient. We saw also the buckling of braces, the column base failure, but in the right figure, this column base is old type, so they are not conforming to the new design specifications. Some statistics in Wajima and Suzu cities, those severely affected area has aging rate of 65 plus for like about 50%, which is very high. Even Japan is known as the world leading aging countries with the 28% the aging rate. But these regions is really high aging rate. And also the vacant houses is the issues, around 20% in this area compared to the 13% in the entire Japan. The building damage rate issued by the Wajima and the Suzu City Council on February 2nd, says destructive the failure was around 35%, which is very, very large. But those are mostly the traditional timber housing. If we go to the site, we see a lot of the new housing designed and built according to the new specifications. They survive without much damage. A little bit about the schools. Seismic upgrading was enforced after the Kobe earthquake in 1995. So in Ishikawa Prefecture, 100% upgrading, around 100% earthquake resistant rate. However, like 85% of public school in Ishikawa Prefecture was damaged somehow. The damage varies from a single glass to structural members or equipment. Damage to upgrade the school building is small, but if we see some the left figure with steel braces, the building was okay, but with some ignorance in the constructions, shear failure of short column occur. This is minor, so the building can be used in a structural aspect. Well, the building was mostly fine. However, there's a gap between the frames because of maybe slip or the failure of the embankment, or some like leaned chimneys, and then those a little bit like non-structural or the damage was notable. Talking about non-structurals, these are the photos for the steel school buildings, but the cladding falling at the higher floor was the severe. Likely this is because of the accelerations, not by the story drift, as the damage was severe at the higher locations. And so we also see some maybe the collision between the ceiling and then the claddings, and then some contents of the buildings jumped out from the windows and then over damaged cladding area. Liquefaction was very, very significant. Even the building was okay, due to this liquefactions, functionality was completely lost. And whereas one area of exceptions nearby Nanao area, there's the hot spring area. So they are rich. They have a lot of a little bit higher taller buildings with more than 10 story. Some of them had the shear failure in non-structural walls or leaning due to, again, the soft soil problems. Still, there's still hotel structural hotels. they typically suffer the damage to the cladding. And then if we see closely the steel members after the failure of cladding or a cover of the motor connections, columns severely corroded due to this near coast environment. Government office shelters was mostly okay, but again, there's a ground deformation around the building was very significant, likely due to strong shaking, of course, and also the softness of the reclaimed land. And then we also see the ceiling failure at some locations. This is gymnasiums of the government-owned building. Some member felt from let's say the light panel material. These light panel material became popular after 2011 Tohoku earthquake. They should be safe even if dropped, but however, like a wire mesh to hold the panel also dropped together, and they are not so light. And also the bracing and the grip member for the seismic resistance, they also fail at some locations. So those are some problems. Maybe the recent problems. About the medical facilities, the major damage in Noto Peninsula, most of the building lost the functionality due to the failure of the water lifelines. Also the power outage and then partial damage to facility and equipment. Earthquake resistance ratio for the disaster-based hospital in this area is 100%. However, they couldn't continue their business. And the hospitalized patient, seriously injured patient, was transported out the area using the helicopters. This is some photos of the building damage, the hospitals, the severe ground settlement, and then slope failure, and some non-structural components failure inside. But we still have not have access to the hospitals for the hearing survey. We plan to have some survey maybe 6 months or 7 months after the earthquake when the medical the system settled down. This is the photos provided by our colleagues in the Kyoto University Hospital. They dispatched to the area as the disaster aid the team. And normally they finish their activities in 1 week after earthquake, but this time they continue for about like 1 month. This is a little bit abnormal because of the need for acute training for the first week. And then later, because of staff fatigues and shortage in affected area, they need to continue this the 3 years of the patient transported from the region to the nearby major city in Kanazawa. In Japan, the hospital has BCPs. The BCPs enforced in 2019, and then for the disaster-based, large scale, the hospitals, they expect to have the higher functionality after the earthquake or any disasters. However, currently, according to the newspapers, the occupancy rate dropped to 20% due to the staff shortage in some Wajima and Suzu City hospitals. The summaries like reinforced concrete building, uneven settlement in area with the soft ground was notable. For steel, the non-structural failure with the exterior walls, and then severe corrosion was a problem. And for the seismically isolated building, I didn't explain much, but there is several, and they worked properly. And for the education and other facilities, earthquake-resistant buildings are effective. And ongoing discussions for the policymakers, they now start to discuss about the review of the regional factor, which is set in like before the World War II. I was 0.9 for Ishikawa, 0.9 for Kumamoto for the strength reductions, but apparently they did not match with the recent earthquake activities. Impact of the foundation pile further due to the soft soils or continuity of the building usage is some the issues under discussions. Also, the probabilistic hazard map in Japan in the left bottom side severely, governed by the Nankai Trough, the big mega earthquakes. But however, like in Ishikawa, the Kanazawa area in the bottom side has larger the probability than the Noto Peninsula. However, in Japan coastline, there's under oceans the faults which was triggered this time. We have those information, but they are not affected, included, reflected inside the probabilistic hazard map. They may need to be updated. And then other serious discussions if we do build back better because areas under depopulation aging. Thank you very much for your kind attentions. This is my talk. Thank you.
Okay, thank you. Thank you so much, Dr. Kurata. I really appreciate the overview that you presented, especially the statistics on with regard to numbers of damaged components and buildings. It was very informative. Now, I would like to move on to our second presentation. This will be on Lifeline systems. The presentation will be given by Dr. Yosuke Ono. Dr. Yosuke Ono from Totora University. Please proceed.
Thank you very much, Bruce, for your kind introduction. Can you see my slide?
We can see it, but you have other windows open in front of it that you need to close.
So,
We see it in your presenter view now. If you can go to slideshow.
sorry, because I have two monitors on my desk, so it sometimes made me confused.
No worries, no worries. If you hit the slideshow mode.
Yes, this one?
Or
this one?
There we go.
There you
Yes, thank you. Excellent.
Sorry for taking time. And again, thank you very much for having me today. So my name is Yusuke Ono from Toto University. Today, I'd like to talk about the lifeline damage caused by the 2024 Noto earthquake. And yeah, okay. So here's the topics I will talk today. In my presentation, I have two parts. Most of my presentation will be used for the lifeline damage and its restoration. But road network, drinking water supply, wastewater treatment system, electrical power supply, and one more thing is I will summarize lessons learned from this earthquake. Okay. So let me begin with the damage to road network. So this picture showed the peninsula mostly affected by this earthquake. So the red colored stars indicate the damaged location of the road network. And that you know that there are many bridges, but unfortunately, no bridges collapsed. Of course, they suffered damage, and some of them need to be repaired. But again, fortunately, there are no collapsed bridge. But however, there are two tunnels that suffered. Their linings dropped off and closed. And also there are many collapse of road embankment. And some locations, landslides or rock falls block the transportation. So generally speaking, no serious damage was observed in road structures, but that were seismically reinforced, earthquake-resistant designed one. They are not. They didn't suffer serious damage, but so as I mentioned, so there are many blocked road. So many small villages were isolated, and this is a point that limited access routes to the damaged area has hampered emergency response and recovery activities so much. So this is the access route immediately after the main shock. So the red line shows the road we could pass through. So as I mentioned, many roads were blocked, and the access routes to the northern Noto Peninsula were very limited. In particular, there was only one route from Nanao City to Anamizu town, so which caused heavy traffic congestion here. So actually, so when I visited Wajima City here, 10 days after the earthquake, I drove more than 7 hours from Kanazawa City. Kanazawa City is the nearest bigger city to Wajima City. And these photos show the damage to road structures. So this is a case of a collapse of a road embankment, and this showed the landslide which broke the transportation. And these photos show the damaged tunnel. The left side one is Otani tunnel, and the right side one is Nakaya tunnel. So you can see the linings dropped off. And next, move on to the damage to water supply. Damage to water supply system occurred in Ishikawa, Toyama, Gifu, and Niigata prefectures. Water disruptions were restored within a few days in all prefectures except Ishikawa. In the northern Noto Peninsula area, a large number of residents still do not have access to tap water. So actually, so restoration efforts activities are still ongoing. So the full extent of the damage to the water supply system is not clear yet. So, but we can say that damage to earthquake-resistant pipes was limited to those involved in massive landslide and other large-scale ground movements. So this map shows the municipalities where water supply was disrupted. You see that the epicenter of the main shock is around here. So the very wide areas are affected by this earthquake. And in this figure, so I put the name of municipalities which was heavily affected. And the figures below the name of the cities and towns, it shows the number of households without water supply. And this slide shows the restoration of water supply. The vertical axis indicates the days spent for restoration of water supply since the main shock. For the case of Toyama Prefecture, it takes 20 days. And for Niigata Prefecture, it took 6 or 7 days, so on. And so we can say that restoration works have not yet been completed in Ishikawa Prefecture, so I didn't put the data on this diagram. And for the case of Toyama Prefecture, it took almost 20 days, but 90% of water outage in Toyama Prefecture were resolved within 9 days. So this is a map of this shows the location of these prefectures. The Ishikawa is here, Toyama is here, this is Gifu, Nagano, and Niigata. And this graph shows the restoration rate of water supply in Noto area, especially particularly northern Noto area. So here's Wajima City, Anamizu town, Noto town, Suzu City. So from the Kanazawa City to Suzu City the distance is about 100 kilometers. And the horizontal axis should indicate the days since the main shock. So look at this diagram. So the green one, this is Ishikawa Town, and this is Anamizu Town, and this Nanao City, Noto Town, Wajima City, and Suzu City. And the restoration of the water supply system in the Noto Peninsula area is taking a long time. So this is happened because the workers must commute from Kanazawa to the disaster area every day, and the limited access routes cause frequent traffic congestion for them. So these factors have hindered the restoration of the water supply system. So they are the reason for why we need so long time to finish restoration of water supply system. And I got statistics from the Niigata City local government. So this is a case for Niigata City. No damage to trunk water distribution pipes. So the trunk water distribution pipes in Niigata City is the total length is its total length is about 340 kilometers. But the water distribution branch pipes were damaged at 92 locations, 92 sites. Major cause of the damage was liquefaction. This table summarizes the damaged water distribution branch pipes in Niigata with the type of pipe. So for DIP, ductile iron pipe, so it suffered 12 failures. In Niigata City, they have a DIP pipe. Its total length greater than 2,000, and the damage rate is given here. The most damage occurred in the vinyl pipe, and the second one is a steel pipe. So the vinyl pipe is not earthquake resistant, but some of the steel pipe may have a earthquake resistant, but they got so many failures. I think I'm not sure the reason. I'm just asking for the local government, but I guess that these are old one, I guess, and maybe so suffered a big, massive ground displacement. And this map shows the location of water leakage in Niigata City. So these how can I say, these circles colored in the sky blue show the location of the leakage, and the size of the this symbol means the number of households with water outage. This plot is on the geography maps. And from this figure, we can say that damage to water pipes in Niigata City was concentrated in the lowland next to the sand dune, and the groundwater level is high around here. And also the pipe damage is concentrated in the man-made land over the old river channel. And these photos show the typical case of damage to water distribution pipes in Niigata City. So most of them are pulled out at the joint. This one, yeah. So maybe it's hard to see, but there's a pull out here. And next, I move on to damage to wastewater treatment system. the wastewater treatment system in Ishikawa Prefecture was severely damaged. Sewage pipes were damaged due to ground displacement, and manholes floated in liquefied areas. 9 sewage treatment plants are reported to they lost their functions. To date, restoration work has not been completed, as well as the drinking water supply system, and the full extent of the damage is not clear yet. In Niigata Prefecture, liquefaction also caused damage to sewage facilities. Data on damage to sewage pipes and sewage treatment facilities being collected. So this is photos provided by Niigata City Government Office. So you can see the water coming through into the sewage pipes through the cracks occurred at the sewage pipes. And this is the case of the manhole, a floated manhole. I think the Masahiro showed the same one. And the next one is the damage to electrical power facilities. So the electrical power outage took place immediately after the earthquake. At the most, 1,600 customers in the prefecture and 35,000 customers in Ishikawa Prefecture lost access to electrical power. The outage was caused by failures in the power distribution network. So there were damaged power plant, but they don't affect this electric power outage. So the damage to power plants are shown here. The Shika nuclear power station was slightly damaged, but not serious. And actually, so the Shika nuclear power station has been shut down since before the earthquake. And another one is the Noto Water Thermal Power Station. This was shut down due to the earthquake. It's damaged. I'm not sure the details, but now the restoration work is ongoing. The authority announced that it is scheduled to be restored by this summer. And this is the damage to electrical power supply in Noto area. So the left-hand side here shows the number of customers without electric power after the earthquake. So most cases of power outages occurred in the Noto areas. In the Wajima City, more than 10,000 customers lost power. And the right-hand side figure shows the restoration rate of electrical power supplied. And the horizontal axis shows the days since the main shock, and the vertical axis shows the restoration percentage of restoration. And so it took 20 days for Anamizu and Noto Town to recover from the blackout, and 60 days for Wajima and Suzu cities. Okay, this is a final slide of my presentation, and here I'd like to summarize lessons learned from the 2024 Noto Peninsula earthquake, but this is from lifeline aspect. So when the earthquake damage occurs in a peninsula region, such as Noto Peninsula, emergency response and recovery activities are likely to be prolonged due to access difficulties. The road network needs to be strengthened, taking into account geographical characteristics. And the second one is the earthquake-resistant water supply pipelines withstood the shaking of the earthquake well. So it shows a good performance, I think. But however, they were damaged when involved in large-scale ground flow, such as landslides and slope failures and lateral spreading due to the liquefaction. If the sewage system does not function, the use of the water supply system will be restricted. Therefore, the seismic performance of water supply and sewerage systems should be improved simultaneously. And so these are just my opinion. of course, I need more analysis and data collection, and I need more discussion with you. Thank you very much for your kind attention.
Thank you very much, Dr. Ono, for a very informative presentation. I found your restoration curves most interesting. This concludes my portion of today's meeting. I will now turn control over to Tali Feinstein, who will lead us in the question and answer portion. Tali, please proceed.
Thanks, Bruce. So we have a bunch of questions from the audience, and I'm going to start with a question for Dr. Kurata relating to functional continuity. So you talked about hospitals and schools, but there's kind of a bigger question on what was the performance of the initiative since that was started in 2018? And also relating to that is what was the performance of base isolated hospitals and structures in general?
Thank you for the questions. The act or guidelines issued in 2018 is quite recent. Still, those guidelines are not used. It's by those the hospital and schools in Noto Peninsula regions. As I explained a little bit about Noto Peninsula, those are the aging, depopulation areas, and it's not so often to see like new type buildings. So, however, the schools and the hospitals, especially schools, they had some measure for the seismical upgrading for the non-structural components. So, like gymnasiums, like large scale, the ceiling failure was less than those in the previous earthquakes. However, still the function was not maintained. But I would say the most important, the significant failure affected the functionality was the water loss. So we went to we visit the site, but we didn't see anybody. Like it's empty, like a ghost town, due to the cut off of the lifeline. So the investigation of the detailed damage to non-structural components still not available as well. And the reports will be published maybe a year later or something. Currently, the Architectural Institute of Japan is trying to do the investigation, but it takes time because nothing actually restored at the site at this moment. For the base isolated structures, the isolation device worked properly. So the structural damage didn't present. However, there's some slight minor damage to the exterior of the at the expansion joint location, but they maintained functionality. However, again, the lifeline was a problem. The water loss prevented the continuous operations of the systems. With the aid of the defense force in Japan, they provide water to the hospital, so they could maintain some functionality, but not 100%. Thank you.
And then you mentioned non-structural components. There's another question about stair damage in the element of that in evacuation and how did that survive? And then relating also to tall buildings and what was the height of the tallest building that got damaged or was in the region?
For the stair damage, I have no information. For the tall buildings in the hot spring area in the Wakura Onsen, they have like 11 to 12-story building. That was the tallest building I've seen at the site.
And then Dr. Ono, there's a general question on liquefaction, and then it will connect to Dr. Kurata as well. Has the region been assessed and mapped for liquefaction potential before the event?
Yes, many places. However, the map did not 100% overlap with the actual damage location, and then the reason is under investigation by the geotechnical engineer.
And then the question that relates to that is, how often did liquefaction affect building stability? And what was the percentage of building affected, or the number of buildings that were affected by liquefaction? If you know.
I have no the statistics. Well, liquefactions does not directly. I think it's I think more lifeline damage. I think Professor Ono can answer better in that. The building has an uneven settlement due to the subsoil, but partially due to liquefaction, but partially just due to the lack of the supporting capacity of the pile at the subsoil. So we cannot distinguish if it's solely due to liquefactions.
So even if there was liquefaction, maybe there would be damage anyway because of the foundation system.
Well, but even the liquefaction occur, we can see you can see the pile or pile cap, but maybe that pile reaches to the ground, then the building remains.
Yes.
However, piping system will be damaged.
And then a question for Dr. Ono is, were there any changes to the gravity flow of water system due to tectonic movements and, I guess, vertical deformation?
So sorry, could you say again?
So was there damage to the gravity flow of the water distribution systems as part of the earthquake damages?
Gravity flow?
So gravity that would flow in the wrong direction now because of changes to the vertical displacement of the ground that would just change the direction of the flow of water systems.
For the case of the water supply system,
Yes.
It pressured, so sometimes it doesn't matter. But for the wastewater treatment system, yes, it caused a problem. Yes, we found some damage.
And then another question on distributed system is, what kind of damage was happening to the electrical distribution system?
Yes, actually, so I don't know the details exactly, but according to my, as long as my knowledge, so it caused it due to the collapse of utility poles, mainly caused by the utility poles damage.
So that was collapse or the failure of the poles?
Yes, yes.
And do you have any inspection of interior infrastructure for fuel, gas piping, or electrical services or HVAC systems in different buildings after this earthquake? I guess it's more for Dr. Kurata.
No, we only conducted the exterior, the inspections. As I explained, when we visited there, it's like ghost town. Nobody. We can't go into the buildings. But the most government facilities and the hospitals and those public built system, they sometimes make a report by themselves, or we will do the hearing survey after maybe several months. Then those information hopefully will be available.
And then a question related to fires. Were there fires that were caused by this earthquakes, and if
yeah.
and
By
were
Professor
there
Scasson.
And were there gas meters gas meter seismic shutoffs that were triggered by the earthquake, and how did they perform? And how long did it take to restore them?
Yes, yeah, they immediately activated after they asked.
So there was no reason to restore them, or how long did it take to restore them after the earthquake? If you know.
No, sorry, I don't have any data right now.
About the fire, let me share my screen. Do you see?
Yes.
Those are in the report I am writing with Khalid, and provided by Professor Nishino of DPRI. There are 17 fire after the event. 15 are triggered by earthquake, strong shaking. And then 2 is by tsunami. And the top is the figure shows the most significant fire damage in Wajima cities. Around like 170, the housing was, I'm not sure that this number, sorry, like a lot of the like housing was burned. And then partly due to the tsunami evacuations, there's a river right next to this fire area. And because of tsunami warning, the firefighters couldn't reach the regions. So that is the one reasons. And the second is, of course, these traditional timber housings are vulnerable, and then those are packed in this area. So due to the multiple reasons, this fire unfortunately spread it quickly after the earthquake. And then the lower is the tsunami triggered fire in the Suzu city. The buildings at that site stands, but due to the tsunami or due to the ground shaking, some collapsed buildings, they gather at the area, and then with some reasons, the fire started the region. But those are something also observed in the previous event, like 2011 Tohoku earthquake. That's a brief summary of the fire damage.
So the next question is on performance of traditional heritage buildings. I don't know if you have information about that. Mostly, assume Dr. Kurata, if you have any.
I recorded some damage there. Most of the traditional heritage building are damaged very severely. And those are made of timber, traditional timbers.
So in the beginning of the presentation, it was mentioned that the economic loss from the earthquake was about $18 billion. Do you know what was the main contributors to that large number of loss?
I don't know. I think Bruce.
Well, let me speak to that. The number I got was from the United States newspapers. They quoted the Japanese government as saying that the direct damage cost was between 8 and 18 billion US dollars. So I quoted the large number for effect, but that's where I got it. So it was from United States news reporting. And again, the numbers may have changed, or that number could be inaccurate, but that's where they came from. Thank you.
So do you have any information on what were major contributors to economic loss in the earthquake? Was it mostly water systems that are still being restored, or damage to buildings, all of the above?
Yeah, but I'm not sure about that. I guess that some part of them are caused by the business interruption.
Okay. There's a question on impacts to port communities due to uplift of the sea bottom, and how it may affect the loss of functionality for the fishing industry.
Yes. It has big impacts to the fishing business. They can't do the fishing right now. They stop their business.
So it still hasn't been restored in any way.
No.
According to the Ishikawa Prefecture, like 87% of the port, like 60 out of 69 fishing ports are damaged by ground uplift, breakwaters, quays, and port roads. So that's the significant loss.
Then there's a question on the seismic performance of buildings and bridges with seismic protective systems. It sounded like bridges generally were not very damaged. So mostly buildings with seismic protective systems.
So only the system I saw is, well, there are many, but base isolate I explained. So that worked. But like oil dumpers in nearby big city for like a relatively high-rise building, a big size building, there are some like toggled braids with the oil dumper and prevented they reduced the story drift. There's some evidence, but in Noto Peninsula, there's not many information about the seismic protect system.
And then there's a question on code changes and improvements to wood buildings, and how did they affect this earthquake? I don't know how much of them were actually implemented. So could you expand on, were they implemented in some of the structures and how they affected the response?
Professor Isoda of the Kyoto University and their colleagues from the AIJ is now conducting the complete survey of the areas and then making the statistics of those buildings damaged by the building period, and those are still under investigations. And then I think you should invite the website so that to have more information. But in Japan, 1918, 81, and also 2000 and 2007, there are big changes. So those I would say those affected a lot to the building housing damage, and then especially the most recent one. Sometimes they have the twice as large strengths compared to the code minimum. They had no damage by shaking.
And then I don't want to keep you here a lot longer, but follow-up question to the traditional heritage buildings is, if there was damage to essentially all of them, do you think there'll be future measures to protect those structurally?
Well, the concept for the heritage is to build back to the original shape with original material. And sometimes they allow some like maybe the hidden braces system or dampers, or maybe seismic isolation sometimes, but it's quite difficult. The cultural importance is the most important thing compared to structural performance, I would say.
Essentially, they won't approve any changes that can be seen. So it's really hard to structurally improve them.
If you have so that interest in that area, the Kumamoto earthquake is one good event to look at. Over the Kumamoto castle was severely damaged, and then they had like 3D scanning of the system, and they now restored some part of the Kumamoto castles, and then they also built the stone back at the stone walls, but they slightly changed something. I'm not sure what they changed, but after the long discussion, they use some modern technology to improve, but the outlook should be exactly same. And then original techniques of construction need to be same.
Yes. Can I say something?
Sure.
Of course.
Yeah, yes. Actually, so I heard that due to this earthquake, Nanao Castle and Kanazawa Castle suffered damage to their stone masonry retaining walls. Stone mason, and so actually, so I'm working for the development to earthquake resistant design of a stone masonry retaining walls, but still underway.
Okay. So I think I will pass it back to Richard, and thank both of you, and I'll probably thank you again. Oh, Richard?
Thank you very much to both of you. That was fascinating. The slides are spectacular, and there's many lessons for us. And I can tell was getting many text messages from my associates on follow-up questions, which I'll coordinate with Tali and with Bruce, and we can send you some follow-up questions, because there's a lot of lessons there that we can learn here. So thank you both so very much for doing this for us. So I'll turn this over to Elizabeth then.
Great, thank you so much, and thank you again to our speakers. And as noted, we will be sharing this information, including the slides from this webinar, on the LFE resource page for this earthquake, which I linked earlier in the chat. And also a recording of the webinar will be posted on our YouTube account within the next week or two. I just want to take a moment to ask folks if you have time to complete the post-webinar survey that will pop up after the Zoom closes in your browser. And you'll also receive a link to it by email tomorrow. And we really appreciate your feedback on these events. You can learn more about EERI at our website and join at that link there. And as Bruce noted, you can find out about upcoming webinars in the Pulse newsletter or by viewing the webinars page on that website. And you can also join the Northern California chapter mailing list for more information. And then just finally, I wanted to acknowledge that our webinar program is supported with funding under a cooperative agreement with the Federal Emergency Management Agency, and that also that the Learning from Earthquakes Endowment and EERI members, like many of you, provide the support that allows us to put on events like these. So thank you very much for that support. And thank you again to our speakers.